Welcome! Today, we're diving into an intriguing problem, number 458, poor pigs. In this session, we'll explore the problem's core concepts and work through an approach to solve it effectively. Let's get started. In this problem, we are tasked with identifying a single poisonous bucket of liquid from a group of buckets. To do this, we can use pigs, but there's a catch: if a pig drinks from the poisonous bucket, it dies. Our objective is to determine the minimum number of pigs required to identify the poisonous bucket within a limited amount of time. The problem provides three inputs. First, the number of buckets, which can range from 1 to 10 to the power of 9. Second, the time it takes for a pig to die after consuming the poisonous liquid, called minutes to die. Finally, the total time available for testing, called minutes to test. The total testing time must always be greater than or equal to the time it takes for a pig to die. The output of this problem is the minimum number of pigs needed to guarantee identifying the poisonous bucket within the testing window. The core of the solution lies in calculating how many buckets a single pig can test within the available time, which depends on the number of tests it can conduct, determined by the ratio of minutes to test to minutes to die. Now, let's explore how to determine the testing capabilities of each pig. If a pig can test t times, it can distinguish between t plus 1 possible outcomes. These outcomes correspond to the pig either surviving or dying at each step of the testing process. Using this, we can calculate the total number of buckets that can be tested with a given number of pigs using the formula t plus 1, p equals buckets, where t is the number of tests a pig can perform, and p is the number of pigs. For example, consider the case where there are 1,000 buckets, minutes to die is 15, and minutes to test is 60. Here, a pig can test 60/15 equals 4 times, which means it can distinguish between 4 plus 1 equals 5 states. To find the minimum number of pigs required, we solve for p such that 5p equals 1,000. In this case, the minimum value of p is 5, as 5 equals 3125, which is sufficient to cover all 1,000 buckets. Let's break down the explanation further with another example. Imagine there are 4 buckets, minutes to die is 15, and minutes to test is 30. Using the same approach, each pig can test 30/15 equals 2 times, meaning it can distinguish between 2 plus 1 equals 3 states. From the formula, t plus 1, p equals buckets, we solve for p such that 3p equals 4. Testing with p equals 2, we find that 3 equals 9, which is adequate to identify the poisonous bucket. Therefore, the minimum number of pigs required in this case is 2. This example illustrates how the number of pigs required decreases when the total number of buckets is smaller or when the available testing time increases, allowing each pig to test more states. To reinforce this concept, let's consider a simpler scenario. If there is only one bucket, the solution becomes straightforward. Since there's no ambiguity about which bucket is poisonous, no pigs are needed to perform any tests. The output in this case is 0. This demonstrates that the problem adapts to edge cases, where the number of buckets is extremely small, as well as to scenarios with more complex requirements. Additionally, the formula, t plus 1, p equals buckets ensures that the solution remains consistent and scalable, no matter the size of the input values. Finally, it's important to understand how edge cases and constraints influence the problem. For instance, when buckets equals 1, the output is always 0 because no testing is required. On the other hand, when the number of buckets is very large, the formula ensures that the solution scales logarithmically, minimizing the number of pigs required as much as possible. Another special case occurs when minutes to die equals minutes to test. In this situation, each pig can only test once, meaning the number of pigs needed becomes proportional to the number of buckets. These considerations highlight how the problem's constraints and formula work together to handle a wide range of scenarios, ensuring an efficient and logical solution. To solve the poor pigs problem, we first consider a brute force approach. The intuition here is straightforward: assign one pig to test each bucket sequentially. If a pig drinks from a bucket and dies, we immediately identify that bucket as the poisonous one. However, this method is highly inefficient. It requires as many pigs as there are buckets, which becomes impractical as the number of buckets increases. Moreover, it doesn't take advantage of the time available for multiple testing rounds. This results in a time complexity of O buckets and a space complexity of O1, but the sheer number of pigs required makes it unscalable. To address this, we look for an optimized approach. By leveraging the ability to test multiple buckets simultaneously and strategically interpreting the results, we can drastically reduce the number of pigs needed. This introduces the idea of using information theory, where each pig's actions contribute valuable data to narrow down the poisonous bucket more efficiently. Now, to develop the optimized approach, we make some key observations. First, a pig doesn't just provide a binary result of alive or dead, it can also encode more complex information by testing combinations of buckets over multiple rounds. The number of states a pig can represent depends on the number of test rounds, plus one additional state to account for survival. For example, if there are t test rounds, a pig has t plus 1 possible states. When we have n pigs, the total number of unique states they can collectively represent is open parenthesis t plus 1 close parenthesis to the power of n. This means that with n pigs in t rounds, we can test up to open parenthesis t plus 1 close parenthesis to the power of n buckets. Using this insight, we can calculate the number of pigs needed based on the time constraints. First, we determine the states each pig can achieve, states _per pig equals, minutes to test / minutes to die, plus 1. Then, using logarithmic calculations, we find the minimum number of pigs required, pigs equals ceil, log, buckets, /log, states _per pig. This approach ensures we can cover all buckets efficiently within the given time. Since the calculations are straightforward, the time and space complexity for this algorithm are both O1. The optimized strategy is clearly the superior choice because it minimizes the number of pigs required while fully utilizing the available time and the combinatorial testing strategy. The key insight here is shifting the problem from a sequential testing mindset to one that maximizes the information gained per test. By strategically combining buckets and interpreting the results, the approach leverages both time and mathematical relationships to achieve efficiency. When comparing strategies, the brute force method is conceptually simpler but grossly inefficient, especially for larger inputs, as it requires one pig per bucket. In contrast, the optimized approach is highly efficient, using far fewer pigs, but it does require a deeper understanding of combinatorics and information theory. The trade-off here lies in the complexity of deriving the optimized solution versus the computational resources it saves. Ultimately, the mathematical relationship between pigs, time, and buckets allows us to minimize resource usage while ensuring the poisonous bucket is identified within the given constraints. In this problem, we need to figure out the minimum number of pigs required to identify a single poisonous bucket among multiple buckets, given some constraints. Specifically, we know that if a pig drinks from the poisonous bucket, it will die after a set number of minutes, called minutes to die. The total time available for testing is divided into minutes to test, which means we can run multiple test intervals within the given time. The challenge is to minimize the number of pigs while guaranteeing that we can identify the exact poisonous bucket within the given constraints. This is a classic optimization problem where we carefully balance the number of pigs, the time available, and the number of buckets to ensure efficiency and accuracy. To solve this problem, we first make some key observations. Each pig can participate in multiple tests because of the time intervals available. The number of these intervals is determined by dividing the total testing time by the time it takes for a pig to die, t equals minutes to test / minutes to die. This means that each pig can provide information across multiple buckets over t intervals. Interestingly, this problem can be reframed as a base conversion problem, where the pigs represent digits and the buckets correspond to numbers that need to be identified. To break it down further, we start by calculating t, the maximum number of tests possible within the available time. Each pig essentially has t plus 1 states, representing the intervals after which it is alive or dead. The total number of buckets we can test with a given number of pigs is t plus 1 pigs, as each pig contributes t plus 1 states, and their combinations multiply. To find the minimum number of pigs needed, we solve the inequality, t plus 1 pigs equals buckets. Using logarithms, we derive the formula pigs equals ceil, log, buckets, /log, t plus 1, which gives us the exact number of pigs required. With this understanding, let's outline the implementation steps. First, we take the inputs, the number of buckets, minutes to die, and minutes to test. From these, we calculate t, which is the number of test intervals and equals minutes to test / minutes to die. Next, using the formula we derived, we compute pigs equals seal, log, buckets, / log, t plus 1. Finally, we return the value of pigs as the result. There are some important insights to note here. The number of pigs required grows logarithmically with the number of buckets, which means the growth is relatively slow even as the number of buckets becomes very large. Additionally, by leveraging the time intervals, we can drastically reduce the number of pigs compared to a brute force approach. Conceptually, this is like encoding the bucket indices in a base t plus 1 system, where the number of digits, or pigs, determines how many buckets can be uniquely identified. This makes the algorithm both efficient and scalable. To implement this solution, we don't need any complex data structures. The key variables are t, which represents the number of test intervals, and pigs, which stores the calculated minimum number of pigs required. Since this is a purely mathematical computation, no additional data structures are necessary. Let's also consider some edge cases. If there's only one bucket, no pigs are needed because the bucket is trivially non-poisonous. If the testing time is shorter than the time it takes for a pig to die, we can only run one test interval, meaning each pig can test just one bucket. In this case, the number of pigs would equal the number of buckets. For a very large number of buckets, the logarithmic growth ensures that the number of pigs remains manageable. As for complexity, both the time and space requirements are O(1), since the solution involves only a few mathematical operations and no iterative processes or extra memory allocation. This implementation solves the poor pigs problem by determining the minimum number of pigs required to identify the poisonous bucket within the given constraints. Here's a step-by-step explanation. 1. Understanding the problem. The problem revolves around using pigs to test buckets in a limited number of time intervals. If a pig drinks from a poisonous bucket, it will die after a specific duration, minutes to die. The goal is to determine the minimum number of pigs needed to identify the single poisonous bucket within the total testing time, minutes to test. 2. Key insight. The number of test intervals is calculated as minutes to test / minutes to die plus 1. This includes the possibility of not testing any more buckets after the last test interval. 3. Formula. The problem can be reduced to a mathematical inequality, test_intervals pigs equals buckets. This represents the number of buckets that can be tested given a certain number of pigs and test intervals. The goal is to solve for the minimum number of pigs required. For logarithmic calculation, using properties of logarithms, the inequality is rearranged to find pigs. Specifically, we compute math.log buckets / math.log test_intervals to determine the base test_intervals logarithm of the number of buckets required. The math.seal function ensures that the result is rounded up to the nearest integer, as the number of pigs must always be a whole number. 5. Implementation. The function poor pigs takes three parameters, buckets, minutes to die, and minutes to test, and computes the minimum number of pigs using the formula derived above. The math.seal function guarantees that the result is an integer large enough to satisfy the inequality. 6. Edge cases. The implementation inherently handles edge cases, such as when buckets equals 1, the result is always 0, as no testing is needed. When minutes to die is equal to or greater than minutes to test, only one test is possible per pig. This solution is both efficient and concise, as it leverages mathematical properties to derive the minimal number of pigs directly without exhaustive simulations or iterations. This is the Java implementation of the LeetCode problem number 458, poor pigs. The logic mirrors the Python implementation, with the primary difference being Java-specific constructs like math.log for logarithmic calculations and type declarations for variables. The formula, test intervals pigs equals buckets, is used to determine the minimum number of pigs required, where test intervals is derived from the total test duration divided by the time it takes for a pig to die. The result is calculated as the ceiling of the logarithmic ratio. In this problem, we are tasked with identifying a single poisonous bucket out of multiple buckets of liquid. To do this, we have a limited number of pigs that can help us test the buckets. The key is that if a pig drinks from a poisonous bucket, it will die after a certain amount of time, specifically minutes to die. The challenge is to figure out the minimum number of pigs required to identify the poisonous bucket within the given timeframe, minutes to test. The clever insight here is that each pig can effectively test multiple buckets by drinking from different combinations of buckets at different intervals. By leveraging this, we can compute the minimum number of pigs needed using the formula, pigs equals the ceiling of the logarithm of the number of buckets, base the number of test intervals. Test intervals are calculated as the total time available divided by the time it takes for a pig to die, plus 1. This approach allows us to systematically test the buckets in a way that minimizes the number of pigs required. Let's work through an example. Imagine we have 1,000 buckets, minutes to die is 15, and minutes to test is 60. First, we calculate the number of test intervals. Dividing the total available time, 60 minutes, by the time it takes to detect poisoning, 15 minutes, gives us 4 intervals. Adding 1 accounts for the initial state where the pig hasn't died yet, so we have 5 test intervals. This means each pig can represent 5 different states, alive after 1, 2, 3, or 4 intervals, or dead. Next, we use the formula to find the minimum number of pigs. We need 5 raised to the power of the number of pigs to be at least 1,000, since there are 1,000 buckets. In other words, we solve for pigs and the inequality 5 to the power of pigs is greater than or equal to 1,000. To make this calculation manageable, we use logarithms. Now, solving the inequality, we find that pigs must be greater than or equal to the ceiling of the base 5 logarithm of 1,000. To calculate this, we use the change of base formula. The base 5 logarithm of 1,000 is equal to the common logarithm of 1,000 divided by the common logarithm of 5. The logarithm of 1,000 is 3, and the logarithm of 5 is approximately 0.699. Dividing these gives approximately 4.29. Taking the ceiling of 4.29, we find that we need at least 5 pigs. So, the minimum number of pigs required for this example is 5. This demonstrates how test intervals and logarithmic growth allow us to minimize the number of pigs needed, even for a large number of buckets. Here's another example to solidify the concept. Suppose we have only 4 buckets, minutes to die is 15, and minutes to test is also 15. First, we calculate the number of test intervals. Dividing the total time, 15 minutes, by the time it takes a pig to die, also 15 minutes, gives 1 test interval. Adding 1 gives us 2 test intervals. This means each pig can represent 2 states, either alive or dead. Next, we use the formula to find the minimum number of pigs. We need 2 raised to the power of the number of pigs to be at least 4, since there are 4 buckets. Solving this, we find that pigs must be greater than or equal to the ceiling of the base 2 logarithm of 4. The base 2 logarithm of 4 is exactly 2. Thus, the minimum number of pigs required in this case is 2. With the output of 2 pigs in the previous example, let's analyze a more complex case. Suppose we have 5,000 buckets, minutes to die is 30, and minutes to test is 120. First, we calculate the number of test intervals. Dividing the total time, 120 minutes, by the time it takes for poisoning to show, 30 minutes, gives 4. Adding 1 gives us 5 test intervals. This means each pig can represent 5 states. Using these test intervals, we apply the formula to find the number of pigs. We need 5 raised to the power of pigs to be at least 5,000. Solving for pigs in this inequality requires calculating the base 5 logarithm of 5,000. Using the change of base formula, we proceed to calculate this value. To compute the base 5 logarithm of 5,000, we divide the common logarithm of 5,000, approximately 3.699, by the common logarithm of 5, approximately 0.699. This gives us about 5.29. Taking the ceiling of 5.29, we find that the minimum number of pigs required is 6. So, with 6 pigs, we can identify the poisonous bucket out of 5,000 within the given time constraints. From these examples, we can extract some key insights. The number of test intervals determines how many states each pig can represent. The logarithmic relationship between the number of pigs and the number of buckets makes this approach highly efficient. Additionally, the more time available for testing, or the fewer buckets we have, the fewer pigs we need. These principles allow us to scale the solution effectively for different scenarios. The time complexity of this solution is constant, or O1. To understand why, let's break it down. First, we compute the variable test_intervals with the formula minutes to test / minutes to die plus 1. This calculation involves basic arithmetic and takes constant time, as it doesn't depend on the input size. Next, we use the logarithmic computation math.log buckets / math.log test_intervals. While logarithms might seem complex, they are fundamentally constant time operations since they depend only on the properties of logarithms and not on the size of the input. Finally, we apply the math.ceil function to round up the result. This rounding is also a constant time operation, as it involves no iteration or dependency on input size. Altogether, every step of the solution involves a fixed, finite set of operations, meaning the overall time complexity remains O1, independent of the input parameters. The space complexity of this solution is also O1, or constant. Let's break this down further. The algorithm only uses a few variables, such as test_intervals, pigs, and temporary values for intermediate calculations like logarithms. These variables require a fixed and limited amount of memory, regardless of the size of the input. Additionally, the solution does not rely on any auxiliary data structures like arrays, lists, or dictionaries whose memory usage might grow with the input size. Since there's no dynamic allocation of memory or dependence on the input size, the memory footprint remains constant. This is why the space complexity is O1. When comparing this optimized solution to brute force approaches, the efficiency becomes even clearer. A naive approach to solving this problem would involve simulating all possible combinations of test outcomes for each pig across all test intervals. This kind of simulation would result in exponential complexity both in time and space. Specifically, the complexity would be O, buckets * test_intervals pigs, which becomes computationally infeasible for large inputs. In contrast, the optimized solution uses mathematical reasoning to solve the inequality, test_intervals pigs equals buckets. By leveraging logarithmic calculations, it avoids simulation entirely and operates in constant time and space, O1. The efficiency comes from the fact that arithmetic, logarithmic operations, and rounding are all constant time operations. With no loops, recursion, or dynamically sized data structures, this approach maintains constant complexity regardless of input size, making it the most efficient and scalable solution to the problem. When solving the poor pigs problem, there are several common mistakes to watch out for. First, overcomplicating the brute force approach can be a major pitfall. Many candidates try to optimize too early without fully understanding the simplest solution, which often leads to confusion and incorrect assumptions. It's crucial to start with the most basic method to build a strong intuition before moving on to optimizations. Another mistake is ignoring edge cases. For example, failing to test scenarios with just one bucket or the maximum limit of 10,000 buckets can lead to solutions that don't work across all inputs. Always make sure to explicitly test these edge cases. Finally, improper time complexity analysis is another frequent issue. Misjudging the performance of your solution, whether overestimating or underestimating, can result in inefficient code. To avoid this, break your algorithm into clear steps and carefully analyze the worst-case scenario for each part. Now, another error to avoid is misunderstanding input constraints. Assuming details that aren't specified in the problem, like thinking the buckets are ordered when they aren't, can lead to flawed logic. The key is to thoroughly read the problem statement and clarify any uncertainties. Another critical mistake is skipping optimization opportunities. Submitting a brute force solution without exploring ways to improve it might lead to failing time limits for larger inputs. To tackle this, take some time to brainstorm alternative approaches. Consider their trade-offs and see if you can refine your solution to be both correct and efficient. To perform well in interviews, there are a few key strategies to keep in mind. First, focus on the problem constraints. These constraints often hold the key to optimizing your solution. For instance, if the number of pigs is limited, think about how that affects your testing strategy. Clear communication is also essential. Walk the interviewer through your thought process step by step, starting with the brute force method and explaining why it's inefficient before presenting an optimized solution.
Recognizing patterns is another valuable skill.
Many problems, including this one, share similarities with common techniques like binary search or combinatorics. Spotting these patterns can help you arrive at a solution more quickly.
Lastly, always be prepared to discuss time complexity.
Interviewers will likely ask you to analyze your approach, so ensure you can justify the performance of your solution. The poor pigs problem is closely related to other LeetCode challenges that emphasize optimization and strategic problem solving. For example, LeetCode 50, the POW-X-N problem, involves logarithmic approaches which can be useful for understanding how to reduce complexity. LeetCode 128, the longest consecutive sequence, tests your ability to use data structures like sets efficiently, a skill that can also be valuable in poor pigs. Additionally, LeetCode 875, Cocoa Eating Bananas, is another example that involves resource optimization, such as using binary search to minimize completion time.
Studying these related problems can provide new perspectives and techniques that may be directly applicable to the poor pigs scenario.
There are several alternative approaches to solving the poor pigs problem, each with its own trade-offs. A binary search approach, for instance, involves systematically dividing the buckets into smaller groups to narrow down the range iteratively. This method is faster than brute force, with a time complexity of O log n, but it requires additional logic to manage these subsets effectively. Another option is the combinatorial approach, which uses mathematical models like combinations or permutations to represent the problem. For example, if each pig can test multiple buckets, you can determine the number of configurations that can be tested within the given time constraints. While efficient for certain scenarios, this method may require more memory or be more complex to implement. Lastly, you could use a dynamic programming approach, where you store intermediate results to handle overlapping subproblems, such as how many buckets can be tested with a specific number of pigs in time. Although this method can simplify repeated calculations, it can be memory intensive, so it's important to weigh the trade-offs when choosing the best approach for your solution.
Great job! We've wrapped up problem number 458, poor pigs.
Today, we saw how logical reasoning and combinatorics come into play for an efficient solution.
Remember to practice related problems and experiment with new approaches. Thanks for tuning in, and see you next time. That's the end of this tutorial.
I hope you found this explanation helpful for understanding the solution to this LeetCode problem.
If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions.
Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have.
Thanks for watching, and happy coding!